Now we will discuss about some topic, we'll understand and we'll try to implement to solve a problem. So the topics that we'll be discussing today, the first one is graph, then the second one is DFS, and we have already talked about recursion. Then we will implement DFS with recursion using Python. Here what we will do, we have the basic understanding, we'll see some real life applications, we'll have some examples for that. We'll have a look at the pseudocode steps in human language to understand what actually happens in the algorithm. Then we'll see the code implementation for the topic. Right. The first thing that we'll be talking about is graph. So this is graph. This is something that should come in your mind when you think about graph. So what is graph? A graph is a data structure which consists of a set of vertices or nodes and a set of edges that connects pair of vertices. So in this picture, these are the nodes A, B, C, D, E, F, and the arrows that we can see here, these are the edges. So this is a non-linear data structure. So I hope you already know about tree or list. This is quite different from that. It has a vast applications in real life. For example, in social networks representing friendships, followers or connections. You have some friends. Those friends are connected with some other friends. And the second level friends may or may not be your friends. So that's like a connection that we can explain with graph. Then in transportation networks, the cities that are connected, they can be explained with the help of graph. Then the same way we can explain computer networks with the help of graph. So there are some differences between tree and graph. So tree starts from the root node and it goes to the child node, the next child node, and until it goes to the leaf nodes. For graph, there is no sequence. It's actually said or decided by the problem which will be the starting node, which is quite different from tree. And also you can see that one node in tree will have children and so on so forth. But for graph, it's actually the edges or the connections. So there are some types of graph. We'll be discussing about two types here. One is the undirected graph and the directed graph. So these are self-explanatory. You can see that for undirected graph, the edges do not have any direction, whereas the directed graph, the edges have directions. So for the connection between A and B, it specifically says the connection is from A to B. So there is no connection from B to A. But if the graph is an undirected graph, we can say the connection is for both sides, A to B and B to A. So this would be the code for graph construction. We're not going to code it, we're going to understand what's said here. So initially, we're creating a class which is graph and we are defining some methods. So the first one is init. It's going to create a dictionary which will basically be the adjacency list. It will have each node and the corresponding neighbors. And now we have another method addEdge which will actually populate the graph dictionary with the nodes and their neighbors. So this is the node and this is the neighbor. So if this node is not in this dictionary, so this node will be added with an empty list, and then the same thing will be done for neighbor. This example is actually an example for undirected graph because we are creating the connection for both the node and the neighbor. Okay. Now we are creating the empty lists. Then what we are doing, we are appending. Basically, we are creating the edge or the connection between node and neighbor both ways. So if we wanted to create a graph that is directed, we would not do the second part. we would not create a list, or I would say an entry for this neighbor. So that would be done for undirected graph. So since this is undirected, so the connection is for both side. We are creating and making an entry in the edge list for both the node and the neighbor. Finally, there is another method, that is print graph. It will simply print all the nodes. Now we will going to learn graph traversal. So there are two traversals that are used. The first one is DFS, the another one is BFS, or breadth first search. But for this discussion, we'll be discussing only about depth first search. This is basically a process which has some sequences, and the sequence would be, if we are visiting a node, we're going to pop the node, we're going to mark the node as visited, and then push all the unvisited nodes connected to it. So this is the first thing that we should remember while using this DFS, and I'm going to explain it further. This would be the example that I will use to explain the whole DFS algorithm. So yes, we have to know what DFS is. DFS is a traversal algorithm for searching all the vertices of a graph or tree data structure by using stack. For BFS, or breadth first search, queue is used. So that's the difference between those two. Now, for this graph, we'll be creating an adjacency list. So what is this? This is another way of creating a graph. So how this is done? For each node, there will be a list that will say how many nodes how many other neighbors this node has. So A is connected with B and F, and we can see A is connected with B and F. This is a list. So that's how we will be doing this for all the nodes. Now, this would be the process. So initially, I'm going to create an empty stack and I'm going to push A in the stack. So here I have decided, as I have previously told, that which node will be the starting node, that will be told or decided by the problem statement. So here, in this case, I'm saying that A will be the starting node and it will be pushed in the stack. Now we will follow the previous step, that is pop the node. When we're visiting it, we are going to mark the node as visited. Then we are going to push all the unvisited nodes connected to it. This is really important. Right. So now we have visited A. We're going to pop A and push B and F. Why B and F? Because B and F are the neighbors of A. So we have pushed them. So we know how stack works, right? If we say pop the node, then it will going to pop the node that was inserted at the end, which is F. So F will be visited as well, and we will pop F. We will insert or push all the unvisited neighbors of F. So let's see who are the neighbors for F. Only D. And that we can see here as well. So D have been pushed. Now we will visit D. So for that we will pop D and push C. Why? Because C is the only unvisited neighbor for D. So C has been pushed. So this is the current status or state of the stack. Now we're going to pop C and push E, because E is the unvisited neighbor for C. Then we're going to pop E, but since E has only one neighbor, that is F, but it's already visited and that's why it's marked. So we are not supposed to push F in the stack again. We're going to return from here, and another element is remaining here, that is B. So we will pop B, but the neighbor of B is C, but C is already visited, so we will not push that one in the stack again. So that's how we have traversed the whole graph using DFS. Finally, the stack is empty and we will return from here. Now, if we compare the traversal order of the same graph using BFS and DFS, this would be it. With the help of DFS, this graph would be traversed and the serial of the visited nodes would be A, D, F, C, E, and B. But for BFS, it would be a bit different. And what's the reason? The reason is very simple. For BFS, we are using queue, and queue use first in first out method. Whereas for DFS, we use stack, and stack uses last in first out method. So based on the entry and the exit, the nodes are visited in the different sequence. Now this is the implementation of DFS with stack, and we're going to understand this code. Now to first implement DFS, we will have to create the graph, and I will use the graph in the example to show how DFS works. So let's create the class. The class would be graph. We are going to first define the methods. This is the init method that creates the dictionary. Now this is the addEdge function, or say the method, and it's really important. As I previously told you, the example was given for an undirected graph. So that's why the function will be changed. And this is the change that I have made. Now we will create another method to print the graph, which will show the adjacency list. And this is the print graph function. Now we will have to create the graph, and for that, let's build the connections. So I have initiated the graph using this class, and I will call the addEdge function with all the nodes that are connected with the neighbors. So here we can see the node and the neighbor, so which will be sent to this function. So now if we look at the picture, we can see that A is connected with B and F. B is connected with C only, and then C is connected with E. And that is how the rest of the connections are built. And this is the way we use the function. Now we will use this print graph to see what has actually been built. So let's say graph print graph. And yes, we have finally found our adjacency list. Now we will implement the DFS. So we are going to define this function DFS that will take the graph and the start node. Because for this problem statement, the start node has to be specified. So what we will do, we'll initially create a set that will be called visited to keep track of all those nodes that are visited. Because if you remember or recall or go back in this video, you'll see that we'll have to keep track of the visited nodes so that they are not inserted in the stack again. So we will create a stack as well, and the first element that will be inserted here is the start node that will be received here. Now we will run a loop, and we will say if not stack, or if the stack is empty, we will break. Now the node that we will get by popping from the stack, that means it will take the last element in this stack, and that will be the node. Now if this node is not visited, the node will be printed. Now what we will do, we will add this node to the visited set so that it's not inserted in the stack again. Now for all the non-visited nodes or unvisited neighbors, for the node will be inserted in the stack. And how we will do that? For neighbor in reversed. I'm reversing this to maintain the order. Here I'm checking whether the neighbor is not visited, and if it's not, then we will append in the stack. Now if we run this, we are not seeing anything because we haven't called the function. Now what we will do, we will call DFS and we will put the graph. And now we have called the DFS, we have put the graph and the start node. Now we have run this, but yes, there is an error. And why is this error? Because if we look here, this graph is actually the object that's been created. So we'll have to call this variable here of the object. So what we will change, we will use the variable or attribute of this object, and from there we'll find the adjacency list. Now if we run this, this is the adjacency list. Let's do one thing. I'm going to comment this out, and this is the sequence of the nodes that are visited. So now let's go back and see whether that matches the serial of the nodes that are visited. Now we can see that the sequence of nodes that are visited doesn't match the example, and that happened because we used this reversed. If we didn't use this, then what would happen? It would actually follow the example that we have provided. Now I'm removing this and I'm running this. Now we can see that this is the sequence that was actually followed in the example. So we have implemented DFS with loop, and now we will implement DFS using recursion. That would be the point of interest for us, to implement DFS with recursion so that we can implement this solution process in a problem in the website.